All right, ladies and gentlemen, so do not disturb is on, so let's get down to business. So we understand that the principles of electron configuration are pretty broad but can be simple at the same time. You just have to be kind of detailed in your approach. The basis of these electron configurations are these three principles, or three rules, you can say. The first one being Aufbau's principle, second being Paul's exclusion principle, and the third being Hund's rule. So we can establish that these electrons exist in orbitals around the nucleus of an atom and see how they align and behave using those three principles. So if we take it back and define what an orbital is these four places around an atom, these energy levels. And the further you go up, the more energy you have and more electrons you get, and the bigger your atom is overall. So we have to understand what an s orbital is. An s orbital is a spherical shaped orbital that can hold one room per se, so essentially has one level, and each level can hold two electrons, one going like this, the other moving downward. And that's what we call the Pauli exclusion principle, which says that these electrons exist with different spins to counteract each other. They spin away from each other because those electrons are negatively charged and they're being smooshed together. So that creates some stress within the orbital, so they have to space out how they can. So that's how they come to get shapes and they get patterns and they feel like this. So p orbitals are the next one up, and p orbitals have three rooms, or three levels, you can say it. And each level, or each room, each bracket I've drawn there, can hold two electrons. One going this way, and one going the other way. But notice how I'm filling them. I'm filling them in a way that seems kind of counterproductive, so it takes longer. And what that is I'm following Hund's rule. And Hund's rule says you occupy essentially the entire orbital before you put something next to each other. So since electrons are negative, we don't want them next to each other, causing stress and problems. So we want to give ourselves as much room as humanly possible. So we fill the floor, quote unquote, before you fill the room. And the d orbital is a pretty big one. It has 5 rooms, and each room can still hold 2 electrons. And a d orbital is kind of a clover shape, so they kind of pack around in there. And the d orbital is filled like so with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And the same with the F1. The F1's where we get kind of really big with 7, 5, 6, and 7. We're going to imagine all of those in a straight line. I just kind of ran out of some space. But the principles are the same. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. With those relative opposite spins. Now, notice you don't have to always fill the room to use the room. So that doesn't make or break your configurations. And to build your configurations in a particular order, we do based on order of fill. Some textbooks report based on order of shed. Depends on your perspective and what you're doing. Here in general chemistry with Mr. Cole, we focus on order of fill. And the easiest way to do that is to use your Aufbau tree. Your Aufbau tree is a really helpful way to organize based on lowest principal energy level first and fill up from there. So to use this Aufbau principle and all these 3 rules, we're going to smoosh them together to make a complete configuration and an orbital diagram. So to do that, I need to establish what element I'm looking at. I'm looking at chlorine. Chlorine has an atomic number of 17. Therefore, I know a neutral atom of chlorine will also have 17 electrons to deal with. And with dealing with 17 electrons, I'm just going to start at the top of my Aufbau tree. I'm over here pointing like you can see, so I'm over here at the top. And then I'm going to fill my way down and then kind of spin all the way back around and fill from there. and then fill from there. We fill at the diagonal to maintain that lowest principal energy level first. We want to fill the lower energies first. So with my finger on 1s, I know the beginning of every configuration is always 1s. I know s orbitals can hold 2 electrons, so there's 2. Here is one orbital filled with 2 electrons. We know this. Let me get a color going here. This being the principal energy level we're talking about. That S is denotating the orbital we're in. And this 2 right here is annotating the number of electrons we're dealing with. So each of these should probably have anywhere from 1 to 14. Just kind of depends on what orbital you're dealing with. To start out, it's pretty straightforward. So I'm going to continue down. I am currently right here. I have filled my s orbital. I'm going to come down to my next one. So that is 2s. I know it has 2 electrons in it. And my goal here, I'm kind of filling in my off-boff tree to get to 17. I'm filling in these orbitals right here until I can get to 17, but I fill them in this particular pattern. I fill them in a particular pattern. So now that I've done 2s, so I've done 1s, now I flow to 2s, then I come back around. My next one I hit is 2p. And p's are different than s's. We've already established that s can only hold 2 electrons. P can hold 6 electrons max. So now that I've done a few orbitals, what I like to do is kind of give myself a check-in. I kind of count up how many electrons I've done. So that way I can kind of make sure I don't do too many or too few. So here I just count up my exponents. I got 2 plus 2 is 4. 4 plus 6, oh, there we go. 4 plus 6 is 10, so I need some more. I need 7 more electrons to get to that full 13. So I still, with my finger on 2p, I haven't went anywhere. I'm going to slide down the tree here and go back to 3s. So 3s, I know 3s can hold 2. Now I slide back around from 3s, I wing it around to 3p. So now I got to take stock again. I've already established that 2, 4, and 6 that's 10 electrons right there. I've added 2 more, so that's 12. So 12, 13, 14, 15, 16, 17. I need 5 more electrons to fill my requirements. So that means my p orbital is partially filled. It can hold 10, it can hold 6 electrons. I'm over here saying 10, it's 6. Your p orbital can hold 6 electrons, but it's only currently sitting with 5. That's fine. It doesn't have to be maxed out. It can have partial filling. So now that I know I'm at my appropriate number of electrons with 17, I'm going to just back count myself really quickly to make sure I didn't miss anybody. So here I know that 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 and 5 make 17. So I know I have 17 electrons. That is my full configuration for chlorine. Now I'm going to move on to the orbital diagram for chlorine. So essentially you just kind of draw what you can expect them to look like. And we've made the standard class that there is electrons filled. I don't care. You can do down, then up, or up, then down. It doesn't really matter as long as they have opposite spins, so you can maintain Pauli exclusion principle. So here is the first energy orbital, or my 1s right here. That's what we can imagine it looking like as it whirls around the atom. And then we move on to 2s. We've established there's 2 in there. So we 1 and 2. Now I know 2p is the next energy orbital I have to deal with right here. So I have to draw what that house looks like. And p orbitals have 3 rooms. 1, 2, 3. I don't love how close that is, so let's give me some space here. There we go. I know this p orbital has 3 rooms and can hold 6 electrons. So 1, 2, 3, 4, 5, 6. So I've done that one, and that one. I've labeled them as such. I recommend you label them just so you can keep track of where you are and what you're doing. So then you're going to come over here to 3s and give it 2. But notice how we're filling them. We're filling the floor, quote unquote, or you fill the orbital before you fill each space, each room. I know my p orbital has 3 rooms, 1, 2, 3. So now I'm going to label it 3p. That's just the label so I can refer back to it in the configuration quickly. So if I want to look at how 3p looks, or 3p says, ooh, as I erase everything, there we go. Well, 3p says I have that many electrons to deal with. I have 5. So with 5 electrons, let's go ahead and fill those in. There's 1, 2, 3, 4, 5. Notice how I filled it. Notice how I filled it. I fill the floor, so I'm going to fill all of 3p. 1, 2, 3. Then I pair up 4 and 5. I'm limited to 5. I don't have to max it out at 6 because I only need 5 to make my 17. Now with the orbital diagram, so that's what I've just drawn here is my orbital diagram. I've even labeled what all the little parts are. With my orbital diagram, I can evaluate what electrons are unpaired. Unpaired electrons just simply don't have a buddy. They're flying solo. So I can say chlorine has 1 unpaired electron. Because when I draw out the diagram, I have 1 electron sitting in the p orbital with no partner. So we're going to do the same thing for gallium. Gallium has 31 electrons. So I'm just going to put my finger right here at the beginning and fill. I'm going to fill down just like I normally would. So I start at 1s. I know s can hold 2, so that's 1s2, 2s2, 2p6, 3s2, 3p6. So here's 18 electrons, I know, because, well, if I just did chlorine, I just found out chlorine has 17 electrons. I put 1 more in that p orbital to max it out, so that means I'm at 17. I need to get to 31. So 3p6, so then I come back here and I move down. So 3p6, then I come to 4s, 4s's. Any s orbital can hold 2 electrons. 4s, and then I swing back around. So I come right here and I swing around. Now I come to 3d. 3d can hold 10, and that's a lot of electrons. I haven't counted up anything in a second, so here we go. I'm going to give myself a reference point here. I know that that is 2, 6, and 10. Then I got 11, 12. 12 plus 6 is 18. 18, 19, 20. There's 2, so I'm at 20. 20 plus 10 is 30. So all the way up to here, I've represented 30 electrons. But I'm not done. I got to get to gallium. Gallium has the atomic number of 31. So in a neutral atom of gallium, I have 31 protons with 31 electrons present. Since it's neutral, the protons and electrons are the same. So I move from 3D, I move down to 4p. So I don't have to fill 4p. It's just got 1 in it. And we're going to do the exact same process to fill in that orbital diagram. So I'm going to move it over a little bit just so I have room. So we got 1s going up and down, 2s, and I just fill in. I know 2p, any p orbital has 3 rooms that can hold 6 electrons. Notice how I'm filling it. And if you think the labeling it makes it messy and unhelpful, that's up to you. I've always found it useful, particularly when I have to evaluate who's unpaired, who's paired, who's higher. 3D, and I got 1 in my 4p here, so 1, 2, 3. I know my p orbital has 3 rooms, or 3 orbitals, I should say. 3 orbitals with 1 electron in it. which that's just reflecting 4p and 4p. Okay? Pretty straightforward. Now, let's do these other two. I got europium here with 61 electrons, so I'm going to do the same thing. Just start over. Start at the top and work my way down and around, 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 and la-di-da until we max out to get to 63 electrons. So let's go. With my finger sitting at 1s, I'm going to go down the tree till I fill up to what I need. My goal is to get to 63 because I've reported a neutral atom of europium, which means I have 63 protons with a matching 63 electrons. It's not any ion business happening, so I don't have to account for more or less electrons. So I can just kind of go. Now that I've done it a couple times, if I don't erase everything, 2p6, 3s2, I can kind of keep it moving. And honestly, a trick I've learned is I've used others to try and help me get the basis of my configuration. Like in the last 10-15 seconds, I've gotten 36 electrons done because I just followed gallium and I applied the configuration for gallium with 31 to my 63 gold. So I just kind of copied it to what I knew would work. But to check myself, let's count it up. I'm going to switch up colors a little bit here to save my brain. So 2 plus 2, this is what I'm counting here. 2 plus 2 is 4. 4 plus 6 is 10. So I know I have 10 electrons here. And 10 plus 2 is 12. 12 plus 6 is 18. 18 plus 2 is 20. So here I'm sitting at 20 electrons. Then I got 30, 36. Oh, there we go. I need some more, but I'm sitting at 4p, so I gotta go down. After 4p comes 5s, and an s can hold 2. 5s, then I swing back around, and here's the tricky part that people tend to miss. So if I'm here, and I swing back around, I don't hit 4f, the first one I come to will be my next 4d orbital. And 4d got 10, so let's do some counting here. That's 36. 36 plus 2 is 6, 7, 8. That's 38. 38 plus 10 is 48. .48 electrons. I gotta keep going. So I'm at 4d and I keep going down. That's 48. And 5p6. 6s2, 48, 49, 50, 51, 52, 53, 54, 55, 56. Uh-oh, we're getting there. And we keep going. So I'm gonna give you a second, pause the video and try and fill in the rest really quick using your off-buff tree. From 6s, we're gonna jump, because 6s follows right here, because 5p, 6s, it comes back up to 4f. 4f, I don't know, let's call it 14. I think that might be too many, so we're gonna pull up our handy-dandy calculator just so y'all can kind of see what I'm counting on my fingers over here. So I know I have 56 electrons already accounted for right here in this area. So I'm gonna add 14 to that, and that puts me at 70. 70 is too many. So I can't use the full 14 or I'll go over. I won't be europium anymore. So we need 4f7. I could have done a whole bunch of different math than what I've just done, but here we go. So 56 plus 7 more would give me my 63. So use your calculator to help you if your brain's short-circuiting like Mr. Cole's is. You can use your calculator to help you see where your goal is. But here you have it at 4F7 for 63 electrons. And we'll do the same thing with our orbital diagram, going up and down, up and down, up and down, all the way until we fill everything out. Or we can look at the periodic table based on its placement and kind of help ourselves out. So we know the periodic table follows trends and relations. I can tell you there are certain zones for everything on the periodic table. There are zones for everything on the periodic table. I need a color y'all can see. Hello. Here we go. So, meow, 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 meow. What I'm outlining now are your s orbitals. All of those elements fall in your s category. Then you got s. Then your next up is p. So everything in the middle here usually will end in a p orbital. Whee. Those are our p. And then you got your d block, our elements, so your d block. So anything in this transitional metal zone right here are d block elements. I don't know if that's making it better or worse, but we're going to smile and wave and keep it pushing. And then down here at the bottom, you got your F block. So if you can kind of conceptualize where elements are, then you can guesstimate where your configuration should end. So I'm going to bring it back to chlorine. Chlorine is number 17. So I'm going to put a blue dot on 17. I found element 17, and that's directly in my p block. So my last orbital should be something p, and lo and behold, it is. Same thing for gallium with 31. I'm going to put a light purple block on gallium. It should have 31 and end in some kind of P. Gallium does end in P. Now it can be 3P, 4P, 5P, whatever. As long as it ends in a P orbital, you should be good. And I can guess that based on the period it is in, it should be 4P because 1, 2, 3, 4. Those are good ways to kind of backtrack yourself. Will it work 100% of the time? No, there are some exceptions to the rules. There are some exceptions to the rule. So just like europium, I'm going to put, I'm running out of colors. Let's put, sure, it's dark blue situation. Europium's EU at 63, so EU be right there. Europium's right there, and we know it's an F block, so F should be the end of my orbital, and it is. Now, if I was to do manganese right here, if I was to draw it out on the periodic table and do the orbital diagram, I would expect it to probably end in something D. So we're going to see if it ends in something D for manganese, because manganese is right there. So let's see if it ends in something, something D. I'm going to see if I can't squeeze it over here on the side to try and validate my hypothesis and the truth behind my tricks. So I got to slide back up to my off-boff tree. So especially when you're doing these, I would write down my off-boff tree and start filling it in just so you can have it. Because the less you have to put into your brain, the better. So I'm going to just key it out real quick. That's 1s2, 2s2, 2p6, 3s2, 2, ooh. Nope. Maybe 3s2, 3p6. Let's see how many I got. 2 and 2 is 4, 4 and 6 is 10, 10 and 2 is 12, 12 and 6 is 18, 18, 19, 20, 3d5 for 25. And lo and behold, it ends in a D block. It's in D block and it ends with D, because I got 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, plus 6 is another 18, 19, 20, and 25. So there you go. That's a little tip and trick on how to build your electron configurations. And then we can use that knowledge of configurations and help save our hands and whatnot, because we do a lot with big elements. Sometimes we have to abbreviate life. Now, if I wanted to abbreviate, let's say I don't have the space on my paper or the time in my test, and it's allowed because you can only use the abbreviated electron configurations with Mr. Cole if the instructions tell you to. So don't get too comfortable using these and relying on them, but you can help yourself out where possible. So I know all of that mess is europium, EU. And europium outlines 63 protons with 63 matching electrons. So I just use my noble gas configurations as a jumping off point. So all of these noble gases have a unique characteristic that they are highly unreactive. They don't do much, but they have quite a bit of electrons to account for. So we can use that core, that noble gas core, as a bouncing off place. So based on where they would go in the off-boff tree is how we can jump off. So helium is our first noble gas with 2 electrons because it's the first one in the family. Helium sits right here. It's a part of the S family since it's red. So it goes here. Helium only has two protons with 2 matching electrons. So that S orbital is full, making it happy and stable. Then we come down and we move to neon. Neon has 10 electrons. So let's see, where do I put neon? Well, I count. If I got 2 here plus 2 here, well, 10 electrons will put me here, soundly and solidly. And then I just can keep going down. The next one would be argon. And then you have krypton. And I'm writing them in these brackets on purpose. I lost my train of thought again. Oh, I need more caffeine in my life. Here we go. All done. So there's basically where all of my noble gases will fall on my off-boff tree. I know they're in all the p orbitals because most of my noble gases are in the p block. So if I wanted to abbreviate this, I would go to the closest preceding noble gas to europium. So europium is an inner transition metal, and it sits firmly in the lanthanide series, so around the row that's got 57 to 86. I can't go to the next noble gas because that's too many electrons. So I have to go to the closest preceding noble gas. So to visualize what I'm telling you, europium's here. That's element 63 in the lanthanide series. I know my lanthanide series sits here on the periodic table. So imagine all of these elements right here, both rows right here, expanding your periodic table out further than it can be printed. So they kind of splice those out down here. Since they're rare inner earth metals, they splice them out for printing and ease of use. So if I know my life lives here with the lanthanide series, the closest preceding noble gas, so I have to backtrack my way all the way around, that would be xenon. So essentially, xenon represents a lot of electrons. Xenon represents 54 electrons sitting at 5p. So at 5p right here, xenon, my noble gas core of xenon, will cover all of that. Ooh, hello? Here we go. Plop, plop. No, that's not what I wanted to do. Come on, iPad, you're making me look bad. There we go. And here we are. So all of those electrons. Let me get this out of here so we're not confusing ourselves. All right, so all of those electrons in purple are represented by a noble gas core of xenon. And then I can just pick it back up at the next energy orbital. Because literally, if I put my finger on xenon, the very next configuration is whatever S. A trick is, after every abbreviated configuration should be some kind of S orbital because you're starting over. And if I want to draw some real quick configurations just to see who's unpaired in europium, I can leave the xenon core there so I don't lose any mass or any electrons. And I got 6s. 6s has one room to fill with 2. Then 4f, 4f, any f orbital has 7 rooms. 2, 3, 4, 5, 6, 7. I've labeled that as 4f. Now I'm gonna fill it. 1, 2, 3, 4, 5, 6, 7. I have 7 unpaired electrons here in europium. And that's pretty much it for the basics of electron configurations and electron diagrams and abbreviated ones. Now I can throw in some ions and stuff where I would change and manipulate the number of electrons. That would make you have to count differently. I hope this helps.